Have you ever stopped to consider the hidden connections in the world around us? What invisible thread could possibly link the immense power of a gleaming jet fighter slicing through the stratosphere, the quiet miracle of a life-saving hip implant seamlessly integrating with human bone, and the profound mystery of a single fleeting atom that exists for less time than it takes to blink? These things seem worlds apart, one representing the pinnacle of engineering, another the frontier of medicine, and the last, a ghost from the edge of physics. Yet, the answer to this riddle isn't found in separate fields of study. It lies hidden in plain sight, within the elegant architecture of the periodic table, concentrated in a single, unassuming vertical column. This is Group 4, home to 4 remarkable elements: titanium, zirconium, hafnium, and the elusive rutherfordium. Together, they are the unsung heroes of our modern world, the fundamental building blocks of high technology, and the subjects of the most cutting-edge science. Each one carries the family name, but has forged its own distinct destiny. As a family, they are defined by their incredible toughness. They are strong, they are shiny, they possess a unique chemical armor, an invisible oxide layer that allows them to resist corrosion with a silent, stubborn resilience that few other materials can match. This shared defense mechanism stems from their identical outer electron structure, a chemical family resemblance that governs their behavior. Yet, beneath this shared chemistry, each one has a unique personality and a set of distinct, specialized talents that have shaped our world in surprising ways. Titanium gives us flight and repairs our bodies. Zirconium safely harnesses the power of the atom. Hafnium makes our computers faster and smaller. And Rutherfordium, the heavyweight phantom, challenges our very understanding of the atom. From the most practical metals to the most ghostly particles, Group 4 tells a complete and fascinating story about matter. So join us on a journey into this extraordinary elemental family. Prepare to meet the metals that are as fundamentally practical as they are profoundly significant. Titanium. Symbol: Ti, atomic number 22. In pure form, it is a stunning silver-gray metal, as strong as many steels, but nearly half the weight. Perfect wherever toughness and low weight must meet. Think about a high-performance jet aircraft. Critical structural parts rely on titanium alloys. So do powerful engines that face extreme forces. Unlike iron that flakes into rust, titanium passivates. An ultra-thin titanium dioxide film is its invisible armor. It shrugs off salt water, acids, and harsh chemicals, ideal for marine applications and desalination facilities. Its inertness makes it profoundly biocompatible. Placed in the body, it is largely ignored. Hips, knees, dental implants, plates, and screws. Moving down one row from titanium, we encounter zirconium, symbol Zr, atomic number 40. As another member of Group 4, it shares many chemical traits with its lighter sibling, but it carves out a distinct and critical identity in one of the most demanding environments imaginable. In its pure form, zirconium is a lustrous, grayish-white metal. Much like titanium, it readily forms an exceptionally stable and protective oxide layer upon exposure to air. This passivation layer is incredibly dense and non-reactive, granting the metal outstanding resistance to corrosion from acids, alkalis, and salt water. But hold a piece in your hand and you'll immediately notice a key difference. Zirconium is noticeably denser than titanium, about 45% more in fact, giving it a substantial, heavier feel. This density hints at its place further down the periodic table, but its most celebrated property isn't its weight. It's its relationship with the unseen world of subatomic particles. Zirconium's primary claim to fame is its indispensable role in the nuclear power industry. The reason is its remarkable transparency to thermal neutrons. In a nuclear reactor, a self-sustaining chain reaction depends on these slow-moving neutrons striking other uranium nuclei. Most metals, like steel, would absorb these crucial particles, effectively poisoning the reaction and shutting it down. Zirconium, however, barely interacts with them at all. This unique property makes it the perfect material for fuel cladding. Pellets of uranium fuel are sealed inside long tubes made of a zirconium alloy. This cladding serves as the first barrier, containing the radioactive fuel and fission products while allowing neutrons to pass freely back and forth, sustaining the chain reaction efficiently. By letting neutrons do their work unimpeded, zirconium alloys enable nuclear reactors to operate safely and economically for years on end, all while withstanding intense radiation and high temperatures. But the story doesn't end there. When zirconium is combined with oxygen, it forms zirconium dioxide, or zirconia, a ceramic that is exceptionally tough and temperature resistant. When grown as a crystal, its stabilized cubic form is famous as cubic zirconia, a popular diamond simulant prized for its brilliance and affordability. However, its true industrial and medical value lies in its incredible toughness. This makes it ideal for high-performance ceramic knives that stay sharp far longer than steel, and for durable, biocompatible dental crowns and implants that can withstand the immense pressures of chewing. Chemically, zirconium's properties almost perfectly mirror those of the element sitting directly below it on the periodic table, hafnium. This similarity means they are always found together in nature and are notoriously difficult and expensive to separate. This separation is absolutely essential for nuclear applications, because while zirconium is transparent to neutrons, hafnium is one of the most powerful neutron absorbers known, a fascinating chemical twin with a completely opposite nuclear personality. Directly beneath zirconium in the periodic table sits its heavy twin, hafnium, element 72. For decades, chemists didn't even know it existed, its presence masked by its almost identical sibling. It was one of the last stable elements to be discovered, a testament to how closely it mimics zirconium in almost every chemical way. Visually, you would be hard-pressed to tell them apart. Both are lustrous, silvery gray metals, but the moment you pick them up, the difference is staggering. For the same volume, hafnium is almost twice as dense, weighing in at a hefty 13.3 grams per cubic centimeter compared to zirconium's 6.5. It's a profound physical distinction hiding in plain sight. This dramatic density difference comes from hafnium packing 32 more protons and many more neutrons into a nucleus that occupies a space of nearly the same atomic size. This counterintuitive similarity in size is due to a fascinating phenomenon called the lanthanide contraction. The effect pulls hafnium's outer electrons in tightly, shrinking the atom and making its chemistry nearly identical to zirconium's. But it's in their nuclear properties where they diverge completely. While zirconium is famously transparent to neutrons, making it perfect for fuel cladding, hafnium is a superb neutron absorber. Its nucleus is like a sponge for neutrons, giving it a neutron capture cross-section about 600 times greater than zirconium's. This one critical difference defines its most important application. That makes hafnium the ideal material for nuclear control rods, the safety brakes of a reactor. They are used to control the rate of fission by absorbing excess neutrons. This is especially vital in the compact, high-power reactors found in nuclear submarines and aircraft carriers, where reliability and performance are non-negotiable. But hafnium's impact extends from the naval fleet to the device in your hand. In the world of microelectronics, hafnium oxide is a revolutionary material. As transistors shrank, the silicon dioxide insulators became so thin that electrons would leak through, wasting power and generating heat. Hafnium oxide, a high-K dielectric, insulates far more effectively, allowing for a physically thicker layer that prevents leaks while behaving like a much thinner one electrically. This innovation was a crucial breakthrough that enabled Moore's law to continue, leading to the smaller, faster, and more power-efficient electronics we rely on every day. From the heart of a nuclear submarine to the processor in your smartphone, hafnium is an unsung hero of modern technology, a heavy element with a mighty impact. Rutherfordium, element 104, or AF. Unlike its neighbors, it is never found in nature. It is forged in particle accelerators by smashing lighter atoms. On rare occasions, nuclei fuse to form Rutherfordium, named for Ernest Rutherford, father of nuclear physics. A discovery dispute settled in 1997. It is intensely radioactive and falls apart almost instantly. Most isotopes last milliseconds, the longest about an hour. Scientists do one atom at a time chemistry to study it. Limited data suggests it behaves like a proper Group 4 member, favoring +4. Rutherfordium has no practical uses. Its value is in testing the limits of matter and our periodic predictions. As we move down from titanium to zirconium, atoms get bigger. Then something strange. Hafnium is nearly the same size as zirconium. Lanthanide contraction pulls electron shells inward. That size match drives their nearly identical chemistry. Density climbs sharply, with hafnium among the heaviest metals. Rutherfordium is predicted to be even denser. All quickly passivate and prefer the +4 oxidation state. Stable oxides, TiO2, ZrO2, HFO2, are ubiquitous. They form similar halides used in metal refining. Understand one, and you have a head start on the others, a testament to the organizing power of the periodic table. Group 4 spans common crustal minerals to exotic lab creations. Titanium is abundant, mined as ilmenite and rutile, converted to metal via the chlorine-magnesium Kroll process. Zirconium comes from zircon in mineral sands. Zircon almost always contains 1–2% hafnium. Their twin chemistry demands hundreds of extraction stages. High purity is critical for nuclear and electronic uses. Rutherfordium is born in accelerators, not mines. Weeks of running can yield only a few atoms, from bulk ores to one-atom synthesis, a spectrum of how elements come to us. Although they sound exotic, Group 4 is all around you. Titanium's strength and low weight power your gear. It resists corrosion and looks sleek doing it. Titanium dioxide makes paints, paper, and plastics brilliantly white. Zirconia crowns, ceramic blades, and sparkling stones. Hafnium oxide enables today's fast, efficient chips. Rutherfordium has no consumer use, but expands the boundaries of what we know. Safety spans from biocompatible titanium to intensely radioactive Rutherfordium. Titanium and zirconium are low toxicity and implant-friendly. Handle fine powders carefully. Hafnium is stable but a neutron absorber. Great for control rods, unacceptable in reactor cladding. Rutherfordium's danger is ionizing radiation, so it is handled remotely in shielded facilities only.